Hello and welcome back to the second episode of my God of War tutorial series. Today we will deal with directions and how their positions are displayed on the radar. So let's have a quick look at our example. In God of War you see the four main directions, which are north, south, east and west, that are displayed as just one capital letter and placed somewhat beneath the actual radar texture. We will make the system much more modular so that you can also add the sub-directions like southeast and northwest and so on. That means that our direction widgets will have a maximum of 2 capital letters. So for example SE for southeast. Before we get to work on the widget, let's go to our radar system folder, and here let's add another subfolder for structures. Go in there and create a new blueprint structure. We'll call that s_direction_info. And in here we will create variables for all of the information that we need about a certain direction that we added. These are only 2 variables. First one will be the name. So north, south, east and west, make that a text. And the second one will be an integer, and that will be the world rotation. So basically what does the rotation of our camera has to be to face that precise direction here. For north that would be 0 degrees, for south something like 180 and so on. Save and close your structure. Then we'll create our widget. So let's go in our subfolder, create a new user interface widget blueprint, and let's call it w_direction. We'll open it up. I already told you that the direction will be displayed on the radar, so this is a sub widget, and that means it has to be desired on screen and no canvas panel is needed. Instead we'll use size box again, then check width and height override, and I'll make mine 32 by 17 pixel. That is just enough space for 2 capital letters, if you're wondering where that numbers are coming from. The only thing we'll need in here is a simple text element. Let's make that a variable, call it text. Default text, let's make that something like SE for southeast. Then expand the font and scale that down to, let's say, 13 maybe. Horizontally, we will align that to the center and vertically to the bottom. When you selected that alignment, that vertically it's not really in the center, and that wouldn't change if we select vertical center here. To fix that, you can scroll down and go to your render transform, expand the transform, and under translation just give it a -1 in Y to move that up a bit. Then we'll also lower the alpha to, let's say, 0.8. 80% of opacity should be enough, and also make the shadow color an alpha of 0.8. just to make it stand out a little bit more. Okay, compile and save. That's it already for designing that direction widget here. Head over to your graph, and this widget needs one variable, which will be the direction info. So what direction was this widget created for? And the type will be the structure we created, so our s_direction info. Let's make it so we have to define this variable when spawning this widget, so instance editable and exposed on spawn. And to update our text to match that, we will implement the event preconstruct. We know that we have to grab our text and set text, then hook that up to event preconstruct, and now we have to figure out what that is. Grab your direction info, break it. Let's expand the default category. We don't need to see our word rotation, only the name is important. And we want to make sure that these are just 2 letters. Currently you could just type in anything for the name. So let's convert that to a string, and then we'll use a function that's called leftChop. Now the count here defines how many letters will be removed. To figure that out, first off of your string here, get the length, which is the amount of letters or characters, and then we will subtract 2. That means that just the first 2 letters will be maintained. Hook that up to the count, and to make sure that these are capital letters, let's call to uppercase, or just to upper. Then you can hook that up for the in text and compile save. Because we implemented that on event preconstruct and not event construct, it also changes in real time the editor here. Let's head over to the designer, then select your w_direction in the hierarchy, expand direction info, and for example if we were to type in north, that would be displayed as NO in capital letters. Compile, save and close your direction widget. We need to be able to dynamically add direction widgets to our radar, so let's open up the radar. That is where our overlay here comes in place. We go to user created and just drag one direction into our overlay. We get it here, and then align it to the center and to the bottom, and there you would have your direction. What you always have to keep in mind when we do the math later is that the position of this widget will be driven by the translation in X. So if you increase that, it would move to the right, and if you lower that, it would go to the left side. Let's remove it. We want to dynamically create them and head over to the graph. It is important that we're able to access them later. So let's create a variable called direction widget. Type for that will be w_direction object reference. And we've got multiple of these. So let's make it an array. Then we will just add one function called addDirection. And that will need one input, which is the direction info that we want to create a widget for. Let's just call that info or direction, really doesn't matter. And then we will create widget. Type for that, of course, w_direction. We'll be asking you for the info, so that's why we needed to create that input. Then let's store that in our array. So get your direction widgets, add an element and hook up the return value. To display it, we have to add it to the overlay. So grab your overlay, add child to overlay, and again hook up the return value as the content. Just like I showed you before, we have to set the horizontal and vertical alignment once we've added that. Otherwise it would be in the upper left corner, which we don't want. To do that, grab the return value of your add child node and set horizontal alignment. Horizontally that was center, and after that set vertical alignment, and that was bottom. After that, let's return. And just in case we ever need to access that return value here, let's drag a pin off of that onto the return value. So that will create an output, and let's just call that widget. Part and save. That's enough for the radar widget. Now the actual radar component has to know about all of the directions it has to display. So let's close the widget here and go to components, PPC radar component. Open that up, close our function, and we need one variable here. Let's call that directions, and that will be an s_direction info array. Make it editable and exposed on spawn. And let's put that in a category called configuration. So that is one of the values that you can change when adding a radar component. By default, we've got the 4 main directions, so let's just add them. We will add 4 elements to our array. First one will just be a capital N for north. World rotation of 0 is fine. Then we've got east, which are 90 degrees in world rotation. Finally, we've got a capital S for south that are 180 degrees, and at the same time minus 180, because that's just how rotation works in Unreal Engine. It goes from 0 to 180 and from 0 to minus 180. And finally, we've got west, and that are minus 90 degrees. We have to spawn the widgets for all of the directions when we're initializing our radar. So let's go here, add some space. After we've set the radar widget reference, we can grab our directions array. And we want to create a widget for every entry in here. So that is a clear hint that we need it for each loop. And in that loop, simply grab your radar widget reference and call addDirection. The info comes from our array element. And once that's completed, we can simply add our main widget to the viewport. Part and save. If we were to hit play, you will see that actually all of the direction widgets were added. However, they are at the same position and just layered on top of each other. For us, that means we still have to define their position based on where the player is looking to avoid them stacking on one place. Close our game preview. To project the player rotation onto a 2D texture like our radar, we need a lot of math. So I will try to break that up into many helper functions in the radar component that you'll hopefully be able to understand. The math here really isn't that easy, so if you have any questions, feel free to post them in the comment section. As I already said, the world rotation goes from 0 to 180 and 0 to minus 180. However, a compass or a radar is more like an actual circle that is looping onto itself. So that would go from 0 to 360 degrees and then back to 0, which means that first off we have to convert a common location, like minus 90 for example, into circle degrees, and that's our first helper function. So let's add one function called rotation to circle degrees. This only converts an input to an output, so we don't need actual logic. Let's make it pure for that, and let's give it one input of type float. That will be the input, so the world rotation, and give it an output of type float called out, so that will be the circle degrees. The positive values, for example 90 degrees, are the same ones on a circle, so we don't have to change anything there. And to make sure that that is happening, let's right click somewhere and use a select float node. Hook up the return value for your out, and the pick A will be that our input is less than 0. If so, we would use that A value. If not, it would be B. So if it is a positive value, simply use the input. If it's negative, it would be as simple as adding a float to your input, which would be 360 degrees. And just to make sure that the value is always in a range of 0 to 360, we will then call modulo, so that percentage character here, and the value will be 360. Hook that up to the A and compile and save. That's it for your first helper function. Let's quickly do an example. So for example, if our word rotation would be 160 degree, it would not be less than 0, and therefore that would just be the circle degrees. However, if it was minus 50 degrees, we would add 360. So the result would be 310, and 310 modulo 360 would still be 310. So that would be the return value here. To see where that direction is on the radar and whether we actually have to display it at all, we need to get the clockwise and anti-clockwise distance between that direction and where the player is facing. So clockwise and anti-clockwise distance of 2 circle degrees. The reason why you have to get them clockwise and anti-clockwise is because later we can simply take the smaller value of these two, and that will make the radar loop onto itself, so that it doesn't matter whether that direction is to the left or to the right side of the player. Okay, let's add a function called getDelta, which is just a synonym for distance or difference. Clockwise is also a pure function, simply returning something. And we need 3 inputs here. So the first two will be 2 floats called A and B, so the 2 values that we have to get the delta between. And the third one will be a boolean called clockwise. Question mark. So if that is false, we get the anti-clockwise delta. Then we also need 1 output of type float, and let's just call that delta. First off, the math here is different based on whether it's clockwise or not. So let's add a branch. Hook that up to the execution. And the math also changes based on which of these values, so A or B, is greater. Okay, so let's use something that is called a compare float macro. So basically, as the name says, you compare an input with another input and you get 3 output execution wires based on whether it's greater, equal, or less. So we want to compare A with B. However, it could be that A is something greater than 360. Same goes for B. So let's simply call our modulo function again and enter 360 to make sure it's in that range. Copy that for B. Then hook up the A to the input and B to compare with. If they are equal, we can simply return with a delta of 0. Copy that return node 2 times for the other 2 paths and hook them up. Let's do the less than path first because that's simpler. So if A is less than B, we would simply drag off of our B modulo 360 and look for minus float and then hook up the A modulo, then connect that to the delta. The greater path is just a little bit more complex. Look for float minus float, then enter 360 as the first value. And what we have to subtract from that is the A minus B. Then plug that in for 360 minus and hook that up to the delta. If you're calculating anti-clockwise, it's basically the reverse thing. So let's still copy our compare float and the 3 return nodes and hook them up. Still, if the 2 values are equal, you would simply return 0. And let's copy our module nodes and hook up A and B, just so we can avoid some messy wires. Again, we will compare A with B. In this case, the greater path is easier. In that case, you would simply use A and look for minus, then connect B and hook that up to the delta. For the less than, we will copy our 360 minus, hook that up to the delta, and then off of B we would subtract A and hook that up to 360 minus. Part safe. So that's it for getting the delta clockwise and anti-clockwise. If you're not exactly sure how the math here is working, simply do some little tests on paper and pick 2 random values on a circle and try to figure out the delta between them. Then you will see that these here are the ways you will figure that out. Now we've got the functionality to convert rotation to circle degrees and get the clockwise delta between 2 circle degrees. The next step would be to convert that into a translation that we can then use for our widget. Let me quickly go back to our radar widget and add a direction onto the overlay. If we make that center and align bottom and then go to the translation, there will be a maximum value. For example, in this case, it would be something like 300, a little bit more than that. Here is reaching the end of the radar texture. So if that translation is anything above that, we would blend it out. We can remove that direction widget, go back to our radar component. Simply wanted to show that so that you know that we need one variable in here, which is the maximum widget translation. Make that a float. Also editable, exposed on spawn. Single variable, not an array. And let's put that in our configurations category. We compile and save. I just showed you what values you could use for that. 300, 330, something like that. I'll just use 320 for that. Compile and save. And now we need the next function that we will call rotations to translation. So in this case, we will use the other helper functions within this function here to project two world rotations, for example, of our camera and of the actual direction, and then convert that into a translation that would then feed into our widget. Let's give that two inputs, which are the rotations that we compare. The type here will be rotator for both inputs. And let's just call them rotation A and rotation B. Let's give that three outputs. The first one will be a vector 2D, which will be the translation. Then we need another boolean called clockwise ? And the third one will also be a boolean called in radar sight ? So that would be false if the translation is greater than our maximum translation and could tell us that we want to hide that widget. Also make that a pure function. If we have a look at one of these rotators here, let's simply break that. And you will get the roll, pitch, and yaw. If I simply hit play and turn around, the only value here that changes is the yaw. So basically that is from left to right. Pitch would be up and down, yaw is left and right, and the roll is something that I can't show you because of the way the third person character works. So we only care about the yaw. Let's convert that to circle degrees. And then we will get the delta clockwise. And we have to get the delta to our second rotation. So break rotator 2, convert that to circle degrees, and plug that in for B. Let's check clockwise. As I told you, we will check whether the clockwise distance is less than the anti-clockwise distance, and we will choose the smaller of the two values. So let's grab your delta and compare float. Hook that up to the execution chain. So basically we want to compare that with the same calculation but done anti-clockwise. So just copy that node, plug in A and B and uncheck clockwise. Then hook it up to compare with. If the clockwise delta is greater than anti-clockwise, I told you we used the smaller values, so then we would use anti-clockwise, which is a bit counterintuitive, but we'll get there. So then let's add a branch. And we want to check whether that delta here, so the anti-clockwise delta, divided by a float, and in here type in 90. I will explain at the very end of this episode where that value is coming from. And then off of it look for less than or equal to float and type in 1. Hook that up to the condition. If it's false, we can return with a translation of 0, 0. Let's just split that. We only worry about x. Y will always stay 0. Clockwise would be false, we're using anti-clockwise, and it would not be in radar sight then if that branch here fails. Copy your return node for the true path. If it's true, it would be in radar sight. And to grab your translation in X, we will use a lerp float node. The alpha would be our delta divided by 90, the A would be 0, and the B is our maximum widget translation. So we are finding a value in between 0 and the maximum translation based on that distance divided by 90. And then we could feed that into a translation in X. However, currently we're doing anti-clockwise. So we would also have to multiply that by another float, which would be -1. And hook that up to X. Let's copy the branch and two return nodes, paste them down here. And we'll hook them up to both the equal path and less than path. On the two lower return nodes, we will check clockwise. And what we do in here is we will get the clockwise delta and also divide that by 90 degrees. And we could copy that less than or equal to 1 node, hook that up to the branch. And for the true path here, the translation in X will still be that lerp node, except we don't need the times -1. Plug that in for X. B would be maximum widget translation, and alpha would be this node here. So the clockwise delta divided by 90. Let's compile and save and quickly recap what's going on in this function. The input here are 2 rotations, A and B. We don't care at all about roll and pitch of these 2 rotations, so we only figure out the circle degrees for yaw of both of them, and then we will check whether the clockwise delta between them is less than the anti-clockwise delta. Based on the result, we take the lower version of the delta here, divide that by a certain value that I'll explain later, and check whether the result is within the range of 0 to 1. If it's not, we use the 2 turn nodes that will tell us that it's not in Radar's side. However, if it is, there are the other 2 nodes with in Radar's side checked, and the translation in X is somewhere in between 0 and the maximum widget translation based on how great that delta value is. Hopefully that's somewhat understandable. Again, if you're not completely understanding that, it's really helpful to do it on paper and just use some examples. There is one last function that we need in here, and that is called update direction widget. So we've got all of the functions in place to figure out the translation. However, we also have to apply that. And first off, drag in your radar. Then we will get all of our direction widgets and run it for each loop. We will call our rotations to translation function, and then it will be asking us for A and B. So A would be the rotation that our player is facing. However, in our component we haven't got access to that. Let's create one variable, call it camera reference, and make that of type camera component object reference. So this one here will be our player camera. We will worry about setting that later. Just drag that in for now. And get world rotation. Plug that in for A, and for B we will make a rotator. So basically B is the rotation of our direction, and to get that, grab your directions array, get a copy of that, add the array index of our loop, then break it. We don't need the name, just the word rotation. Convert that to a float, and plug that in for yaw. Again, roll and pitch are not important for us. So that here is the translation that we then have to apply. However, let's do a branch off of the in Radar's side first and hook that up to the loop body. So now we will worry about hiding and showing that widget based on whether we can see it or not. If it's false, it would be as simple as grabbing your array element and look for is visible. Add another branch. If that is true, our direction widget would be shown even though its position is nowhere on our radar, and that means we would then call set visibility and set it to hidden. We don't have to update the translation if you can't see it anyways. However, if it's true off of our array element, set render translation and plug in the translation from a node down here. Then also add a branch. Condition will be whether our widget is visible. And this time, if it's not visible, we want to show it. So copy here set visibility to the false path, hook up the array element, and select self-hit test. Pound save. So finally, we've implemented all of the helper functions we need in here. However, the question remains when we have to call this update direction widgets function. If we did it on event tick, that would be a complete waste of performance, because if we have a look at our game here, I could just stand still, not turn around or anything, and it would still update every frame. So that's very heavy on performance. We will only change it when the player changes the facing direction. So let's head over to our event graph and let's add a custom event called onPlayerTurned. It would also be a waste of performance if we updated the positions of the widgets, even though our radar isn't visible at all. So first off, let's grab our visible boolean, add a branch. And if it is visible, we will call update direction widgets. We also have to update it the first time when we've created all of the widgets. So right here, before we add to viewport, simply call update direction widgets. Still, our component doesn't know about that camera reference here that is used for the calculation. So let's change that by going to our initialize radar custom event and give that 2 inputs. The first one will simply be an actor object reference. Let's call that player. And the second one will be camera. And let's make that a camera component object reference. Then before we create the main widget, let's promote the player to a variable called player reference, set that, and after that set the camera reference to the input. So basically when we initialize a radar from an outside class, we would tell it about the player that it was created for and the camera that it should use for calculations. Because these are some internal reference, we can make the player reference private as well as the camera reference. And let's just put them in a category, so player and camera, and also move the player reference in there. Compile and save, and that's it for everything within that radar component. The player still has to tell our radar about these two values here, so player and camera, and call the onPlayerTurned event when doing so. So let's close our radar and open the third person character. Let's go to event begin play first, because what you will see is that there are two new inputs here called player and camera on that initialized radar call. So drag in your follow camera, hook that up as the camera, and for player simply get a reference to self to update the direction widgets when the player is turning around. Fortunately, under mouse input, you've got the input axis turn, which is responsible for that. Currently, the only thing it's doing is adding the controller yaw input, so that's responsible for your camera turning around. However, we also want to grab our player radar and update direction widget. If you were to just leave it like that, that would still be a complete waste of performance, because that axis event here is called per tick. So even if you're not even trying to turn around, it would be called with an axis value of 0. So what we will do is grab our axis value and let's check that it's not equal float, leave it as 0, then add a branch, and only if it's true we will update the direction widget. Compile and save. Let's play and see whether that's working. Okay, so now I'm in play mode. If we're just facing straight, we're seeing north here, and if I turn around, here it is east, then south, and finally west. And if we turn around more, it will loop onto itself and you see north again. So that's working perfectly. Also you see that if the directions are somewhere completely else, you don't see the direction widgets. So for example, currently only seeing north and east, and now north is hidden, but south appeared. So that's also working fine. The only question that remains is if we have a look at our radar component, in our rotations to translations function, there is that magical 90 numbers. It seems like it's working perfectly fine, however you probably don't know where it's coming from. So let's have a look at our third person character, at the follow camera, and here you've got the field of view. Currently that's set to 90 degrees. So the field of view is just the amount of degrees that you're able to see using your follow camera. Good for us that it's set to 90, otherwise our system wouldn't work. To fix that issue, what you can do is replace that 90. So simply grab your camera reference and get the field of view variable and plug that in for the two division nodes here. We then compile and save and play. Everything still works fine. However, what you can very simply do now is go to your follow camera and maybe let's bump up the field of view to 135 degrees. Compile, save and play. Now you see that the camera is way back and it kind of looks distorted. However, our directions are still properly displayed. So if we turn around here, that is east, then south and west. That looks very strange though, so let's reset it to 90 degrees. And the last thing I want to show you is when you go to your player radar, you've got a configurations tab with the directions. Let's just add an element here and call that northeast, so NE. East would be a rotation of 90 degrees, so northeast would be 45. And if we compile and save, you would also see that appearing here. So if you want to, feel free to add the other subdirections. That would be southeast, southwest and northwest. Alright, that's the end of this episode. Our directions are working properly, so in the next one we can apply that math we just coded to drive the position of quest markers and also worry about distance between markers and the player. So see you in the next episode.